Great. Our next speaker is Amalee Wilson from Stanford University. Her field is computer science, and her advisor is Clark Barrett, and her practicum was at Pacific Northwest National Laboratory.
All right. So thanks for the introduction. Today, we're going to be talking about partitioning strategies for distributed SMT solving. And SMT here, to expand the acronym, it means satisfiability modulo theories. So can I just hand raise if you've heard of an SMT solver? Okay, that's what I thought. So we're going to talk about exactly what they are, and then real quick, we're going to I promise this is going to make sense. So how do we make a Boolean abstraction of a math problem? Okay, so let's say you have some math you want to do, and you know that x is greater than 50 or y equals 12. Cool. We can encode that as Boolean variables. So Boolean variables can be either true or false, and we're going to have, A or B. And then you want to add something else there. X plus y is greater than 100. We can encode that as another Boolean variable. Cool. So now you have a Boolean abstraction of your math problem. Why am I talking about this? So the input to an SMT solver looks a lot like the thing on the left. And internally, it's going to have a representation like the thing on the right. And what it's going to do is there's going to be this interaction between your internal SAT solver, which is solving the thing on the right, and the theory solver, which knows about the representation on the left. So you can do more than linear integer arithmetic with SMT solvers. And why would you care? What might you do with them? Let's find out. Okay, so why would you want to use them? Why would you want to make them go faster? You can do things like hardware model checking, software model checking. You can find bugs in your hardware and software designs. They're used in security applications, program synthesis, and any kind of optimization problem that you have, such as, say, maybe qubit placement on quantum hardware. You can do that with SMT solvers as well. All right, and then just as a fun little bonus for anyone who is I don't care about SMT solvers, try to figure out which of these images were not generated by DALL-E. So think about it. Okay, so when you have this application doing all this cool stuff I talked about, you're going to be calling an SMT solver. Maybe you do it once, maybe you do it a lot of times, but unfortunately, as amazing and cool as SMT solvers are, they are the performance bottleneck for these applications, which is sad. And then, just to be absolutely clear, the SMT solver is taking the set of logical constraints that you've given it, and it's trying to determine, can these all be satisfied at once? Okay? So there's this cool thing called portfolio solving, which is how we try to, expand that bottleneck a bit. And instead of your application calling one SMT solver, it's going to call a whole bunch of them. And you can run these in parallel. But the thing is you're basically crossing your fingers and hoping that you get lucky, and one of those sequential executions that you're running in parallel goes fast. And this is like the current state of the art. It does really, really well, surprisingly well. So we're done, right? That's a quick talk. Not quite. So we're going to be limited by our best sequential execution of any of these individual solvers. And so we're not, in this case, doing a divide and conquer strategy, which is what you might be familiar with in HPC. Instead, we're just, like I said, hoping we get lucky. But we can do better. Yay! So how do we do better? I kind of alluded to it. We're going to take our hard SMT problem, and we're going to divide it up into some hopefully easier subproblems. It turns out this is super hard. So you might think, divide and conquer, no big deal. It is a big deal. You can actually make your performance worse if you do this the wrong way. So that's bad. Okay, so rest of this talk, we're going to talk about partitioning strategies. So how do we divide up that problem? And then I'm going to interleave the evaluation with a discussion of some advanced portfolio techniques, which we use to get much, much better performance. And probably talk about a bunch of random stuff along the way, because this is, computer science is complicated, and there's lots of words that I have to remember that not everyone knows. Okay, so how do we do parallel SMT solving? Our input to a partitioning solver, which is what's going to make the partitions. This is a sequential step. It's a partitioning strategy, and we're going to talk about those in a minute, so let's just put a pin in it. And our input formula, so our set of constraints that we want to try to solve in parallel. All right. The partitioning solver creates what are called partitioning formulas, and these partitioning formulas, we're going to use them to create our partitions. And don't worry about the mathy looking stuff. Basically, this is just how we can divide an SMT problem, okay? So now that we've constructed our partitions, here comes the parallel step, the fun part. We're going to run all those partitions on different cores. Great. So parallel SMT. Now everyone knows how to do it. Okay, so for our partitioning strategies, we did this thing. So this work was actually recently accepted to a top conference in automated reasoning. Really excited about that. So what we do is we look along 4 dimensions for how we can partition these problems. And the first 2 are going to be our what. So what are those partitioning formulas made out of? Like, what exactly goes into them? And we do this with by varying the atom source and the atom selection heuristic. An atom here is just one of those Boolean variables that represents a mathematical expression. Next step is how. So how exactly are we putting these things together to create our partitioning formulas? And we do that with our partition type. And lastly is when. So that's our partition timing. In our partitioning solver, that first step, when do we want to create the partitions? And then how are we going to figure out when? All right, so here comes the evaluation part, which is we're going to talk about our partitioning strategies and then discuss the portfolio stuff. So we had 214 challenge benchmarks. We call them challenge benchmarks because they are hard. So they're very tricky for SMT solvers. A sequential solver fails most of the time. And let's see what happens. So first we're going to talk about when. So trying to determine when should we partition. And what we have, so you're going to see this metric a lot. It's called the par2 score. It's going to be the y-axis on all my graphs. Par2 score is the time it took to solve the problem plus 2 times the timeout of the number of unsolved problems. And the timeout just means that, we said, we'll give you 1,200 seconds to try to solve this. And if you don't solve it, oh well, just stop, because it'll run for days and days or until it crashes. Okay, and this first table is on a subset of the benchmarks, but all the other ones are on the whole 214 challenge benchmarks. So we find if we wait 1 second, we can solve 40 problems. We have a decent par2 score. If we wait 3 seconds, we have a better par2 score, and we solve 42 problems. Lower is better for par2. But if we wait even longer, then we see diminished returns. Okay, so we don't want to wait too long because we're wasting time if we do that, but we want to give the SMT solver a little time, the partitioning SMT solver a little time to figure out what it's doing. Okay, so next step, how should we decide when 3 seconds has passed? So we can do this in 2 ways. We can either use a timer that's literally counting wall clock time, or we can count the number of checks to a certain, the number of calls to a certain function, which is called check. And for some of our strategies, we find, again, lower is better, and the x-axis is our number of partitions, which in this case is also our number of cores. And we find that using just wall clock time is better. And same thing for a different strategy, and for our final strategy, it's kind of inconclusive. So we can talk more about that if you have like a question. But we decide, okay, we'll just use wall clock time for all of them. And again, what we're trying to do here is say, like, okay, how should we explore this space? How should we narrow down the whole partitioning space, this like 4 dimensions, to figure out a good way to make really good partitions? Okay, so next step is our what and how, which we're kind of smashing together because the cross product is only 6 things. And we want to figure out, can they do better than random? So, if you have a random strategy that can do better than our more sophisticated strategies, you should just use random. And what we found is that half of our space for partitioning strategies does about the same or better than random, and the other half, they're not so good. So again, you can see as we increase the number of partitions, the performance tends to get better, but not for all of the strategies. So we get rid of those that are not good. And we also compare to OpenSMT2, which is a different solver that lets you do partitioning. And what we find, okay, big fun graph here. What we find is that we outperform, our top 3 strategies outperform 2 of their strategies. But one of theirs is much, much better, which is this bottom line here. As I said, lower is better. So that's too bad, but it got us thinking. What if we combine some of our strategies and see if we can do better? And this is not, it's not obvious that this would work, because to be fair, you would have to use the same number of cores, and it's not clear if creating 2 sets of 4 partitions is going to be better than just creating 1 set of 8. But guess what? We find that it does do a lot better, and I'll explain how. So we call this a partitioning portfolio, and you have your input formula, and you're going to create, say, n over 2 partitions with partitioning strategy A. You create n over 2 partitions with partitioning strategy B. You run these in parallel, and you imagine that these are entries in your portfolio. So whichever sets of these finishes fastest, they win. Okay? So as I kind of alluded to, we do improve performance by doing this kind of thing. And we find that compared to the best OpenSMT2 strategy, we can actually do better if we combine some of our approaches. And later we go further and we just say, you know what, we can probably eventually do as well as OpenSMT2, so we'll incorporate their strategy into our portfolio. All right, so non-obvious result, if you use multiple partition strategies but the same number of partitions or cores, then you end up getting better performance. That's very exciting. Okay, so then we started thinking, how do we maximize this diversity in our partitioning portfolio? And I came up with this cool thing called a graduated portfolio. So if you remember nothing else, I think this is the cool thing to remember because this is great. So we're going to use, if you're just using one partitioning strategy, with your partitioning strategy, you'll create 2 partitions, and you'll create 4 partitions, and you'll create 8 partitions, and so on and so forth. And then each of these sets becomes entries in your partitioning portfolio, and the total number is still less than or equal to n. There's a thing when you're summing up powers of 2 where you can't quite get exactly to that power of 2, but it's still going to be a fair comparison. So we took this graduated portfolio strategy, and we applied it to the OpenSMT2 strategy, completely unmodified. So we're not touching their partitioning strategy. We're just telling them how many partitions to make, and we're creating a portfolio. And we find that it improves the performance by quite a lot. And some of you may be asking, okay, is this statistically significant? The answer is yes, with a super, super small p-value, which is very exciting. So we do quite a lot better with this graduated portfolio strategy, but what else can we do? So we say, okay, we have this recommended portfolio, which is going to combine the approach of a partitioning portfolio where you use more than one strategy, and the graduated portfolio where you create 2, then 4, then 8 partitions. So we'll create 2 partitions with strategy A, 2 partitions with strategy B, so on and so forth. And guess what? We still do better. And the total is, once again, less than or equal to n, where n is the number of partitions. And so what we find is that our recommended portfolio actually does quite a lot better. So it's doing way better than the partitioning strategy. It's doing way better than the graduated portfolio version of that same best partitioning strategy. And this is really exciting because it's using some of our partitioning strategies. Okay, so last thing, I think this is my last graph on this. How do we make a hybrid portfolio? So it's called hybrid because we want to use the current state of the art, which is just your regular portfolio that you would normally use. We use our recommended portfolio strategy for half the partitions, or half the number of cores that are available. And then the other half, we use scrambles. I'm not going to talk about what scrambling means, just suffice to say it's a way of doing portfolio solving. All of these are entries in our advanced portfolio. And again, we obey that we're not going to exceed the number of partitions or cores that are available to us. Okay, so fun graph. This is the last graph. And I'm going to walk through it line by line because it's a lot of lines. So just for fun, plotted on the very top left, all sad by itself, is what happens if you solve these problems sequentially. And this other line, this dotted line, is our standard portfolio, which is a scrambling portfolio. And if we plot now the recommended graduated portfolio, we can see that we're doing you know, maybe the same for lower number of cores, a little better for higher number of cores. That's good. But what we find is that when we combine these approaches, we actually do quite a bit better than either individual approach. So this suggests that they're complementary. Exciting. And then there's this other really cool thing that you can do. It's a super simple optimization where it's called multi-job. And you can schedule your partitions on the available cores. So you don't have to, you know, if you make 100 partitions, some of them may solve in like a second, while others, you know, take a really long time. So when we use this very simple multi-job optimization, we see that we continue to perform a lot better. And note that this multi-job optimization cannot be done on a standard portfolio. It can only be done on strategies that include partitioning. Okay, and I just want to highlight real quick that, you know, maybe we're used to seeing better scaling in HPC applications, but each problem, like each single extra problem that we solve is actually a huge step forward because these are very hard problems that are previously unsolved by all of our strategies. You can see we go from solving 54 when we run them sequentially. When we have multi-job, which can be improved on, by the way, we can solve 114. So this is the last slide. This is the end of the talk. Real quick, future work, we're advancing our portfolio strategies and partitioning strategies, working on a better multi-job, and looking at recursive partitioning. So the end.